Let's look at the graph of rational functions. So we're going to look at a series of steps in order to graph a rational function. I did upload a foldable or a handout to Blackboard that summarizes these steps. I did not create it, but I cannot find it online anymore, so I can't give it truly proper credit for it, but I did not create it. When we're graphing rational functions, we will look for wholes. We'll do that by factoring completely the numerator and the denominator and canceling any common factors. The factors that cancel form holes in the graph. So to find the x-coordinate of a hole, set the canceled factor, or if there's more than one, each of them, equal to 0 and solve for x. We'll substitute that result, that value we found for x, back into the simplified form of the rational function in order to find the y-coordinate of the hole. And hole is just a simpler way of saying removable discontinuity. It actually looks like a hole on the graph. Then we will find vertical asymptotes by setting the simplified denominator equal to 0. We've been doing that already. Then we'll find the x-intercepts by setting the numerator equal to 0. So technically we're setting f of x or y equal to 0, but then with a rational function, that simplifies to just looking to see where the numerator equals 0. Then we'll find the y-intercept by substituting 0 in for x and solving for y. We'll find the horizontal or oblique asymptotes going through the different possibilities, and we'll use all of those results to graph, and then from the graph we will identify the domain and range. So let's look at f of x equals x squared plus x minus 12 over x squared minus 9. Factoring, we get x plus 4 times x minus 3 over x plus 3 times x minus 3. The x minus 3's cancel, so our simplified form is f of x equals x plus 4 over x plus 3. Let's find our hole or removable discontinuity by taking the factor that canceled, the x minus 3, and setting it equal to 0. Solving for x, I'll add 3 to both sides, and x is 3. That's the x value of our hole. Now we will substitute 3 in for x in the simplified form. So we have y equals 3 plus 4 over 3 plus 3, or y equals 7, 6. So the coordinate of our hole is at 3, 7, 6. I'm going to put that on my graph. So it should look like an open circle. Next, let's find the vertical asymptotes. So we're looking at our simplified denominator, which is x plus 3, and we're setting that equal to 0. Solving for x, subtracting 3 from both sides, x equals negative 3. So our vertical asymptote is at x equals negative 3, and I can draw that in as a dotted line, a dotted vertical line. Our x-intercept, let's set the numerator, x plus 4, equal to 0, and solve for x. Subtract 4, we get x equals negative 4. So we have an x-intercept at negative 4, 0, and I can plot that point. Y-intercept. Let's take the simplified form of the rational function and substitute 0 in for x. So y equals 0 plus 4 over 0 plus 3, which is 4/3. So we have a y-intercept at 0, 4/3, and we can plot that point. Horizontal asymptote. Well, the degree of the numerator was 2, the degree of the denominator was 2. They are the same, so we need to take the ratio of the leading coefficients. That is 1 in the numerator, 1 in the denominator. So y equals 1 over 1, or y equals 1, is our horizontal asymptote. I can draw that in as a horizontal dotted line. Now, we can see from our points where we have our branches. And we can see that the asymptotes break our graph into 4 different quadrants. We will have a branch up here where our curve is approaching the vertical and horizontal asymptotes and goes through the point, and where where the hole would be. And we have another branch down here. I'm not looking for exact curves here, like we don't need to figure out how close it gets into the asymptotes. Having those feature points like the x-intercept, y-intercept, holes, that is enough at this point. So this is our graph, or a reasonable approximation of our graph. From here we can now identify our domain. So we first know that where we have a vertical asymptote at x equals -3, that -3 is excluded. Oops, and I somehow did not put a slash through it, so let me add that in. So the domain is where x does not equal -3, and also where x does not equal 3, which is where our hole is, our removable discontinuity. We do not have a point there, so it's not part of our domain. For our range, we can see that we are excluding where our horizontal asymptote is, so y does not equal 1, but we are also excluding the y value of the hole, which is 7, 6. So the range is the set of all y such that y does not equal 1 and y does not equal 7, 6. Let's look at a second function. F of x equals 2x squared minus 8 over x squared plus x minus 6. Let's factor our numerator by factoring out a GCF. So 2 times the quantity x squared minus 4. My denominator factors 2x plus 3 times x minus 2. My numerator we can continue to factor to 2 times x plus 2, x minus 2. My denominator stays the same, x plus 3 times x minus 2. And we can see that our x minus 2's cancel. And our simplified function is 2 times the quantity x plus 2 over x plus 3. To find our hole, we'll set the cancel factor, which is x minus 2, equal to 0. Solving for x, we find x equals 2. That's the x-coordinate of our hole. Let's substitute that into our simplified version for x. So y equals 2 times the quantity 2 plus 2 over 2 plus 3, which is 8/5. So the coordinates of our hole are 2, 8/5. And I can draw that in about. So that's an open circle at 2, 8/5. Let's find our vertical asymptote. So we'll take our denominator, x plus 3, set it equal to 0. Solve for x. X equals -3. And that is our vertical asymptote. We can draw that in as a vertical dotted line. So x equals -3. Our x-intercept, we'll take the simplified numerator and set that equal to 0. So 2 times the quantity x plus 2 equals 0. I could divide both sides by 2 and get x plus 2 equals 0. Solving for x equals -2. So my x-intercept is at -2, 0, and I can plot that. The y-intercept, we'll put 0 in for x. So y equals 2 times the quantity 0 plus 2 over 0 plus 3, which is 4/3. So we have a y-intercept at 0, 4/3. Can plot that. Let's find our horizontal asymptote by looking at the degrees of our numerator and denominator. The degree of the numerator was 2, the degree of the denominator was 2. So ratio of leading coefficients will be y equals 2 over 1, which is y equals 2. That's where I can draw my horizontal asymptote. We know for sure the quadrant where we have one branch of our function, we can draw in this branch. And it would be a good guess to say it's the opposite quadrant, so quadrant 2-ish, if we were truly in quadrants. But to check, let's check an x value to the left of our vertical asymptote. So our vertical asymptote is at x equals -3. So let's figure out what f of -4 is. So 2 times -4 plus 2 over -4 plus 3, which is -4 over -1, or +4. So we have a point at negative 4, 4. So we know that we are indeed in this section for our second branch. We can draw in a curve that is bounded by the asymptotes. So this is a good enough approximation for our graph. Our domain, we know, will not include the x value where the vertical asymptote is. So the domain is the set of all x's such that x does not equal negative 3. It will also not include the x value of the whole, so x does not equal 2. Our range will be the set of all y values such that y does not equal 2, which is where our horizontal asymptote is, and y does not equal 8/5, which is where our whole is. It's the y value of the whole. Okay, let's look at a third function. F of x equals 5x minus 10 over x squared plus x minus 6. Factoring in the numerator, I can factor out a greatest common factor. The denominator factors 2x plus 3 times x minus 2. We can cancel out the x minus 2's, and we're left with 5 over x plus 3. To find our whole, let's set the cancel factor x minus 2 equal to 0. Solving for x equals 2. That's the x coordinate of the whole. Let's substitute that into the simplified function. So y equals 5 over x plus 3, or 5 over 5, which is 1. So the coordinate of our whole is 2, 1, and I can draw that in. Let's find our vertical asymptote by setting the denominator x plus 3 equal to 0 and solving for x. We get x equals negative 3. We can draw in a vertical dotted line at x equals negative 3. For our x-intercept, we'll set the numerator 5 equal to 0, but 5 never equals 0, so that means we have no x-intercept. For the y-intercept, put 0 in for x, so y equals 5 over 0 plus 3, or 5/3. So we have a y-intercept at 0, 5/3, and we can plot that point. So looking at the degrees of our numerator and denominator, the degree of the numerator is 1. The degree of the denominator is 2. That means the degree of the numerator is less than the degree of the denominator. That means my horizontal asymptote will be y equals 0, which is the x-axis. So I'm drawing a dotted line there. That makes sense why we don't have an x-intercept now. We can draw in one branch right here to make sure we know where the other branch is. Let's look at an x value to the left of the vertical asymptote. So if we look at f of negative 4 and substitute that in, 5 over negative 4 plus 3 gives us 5 over negative 1, or negative 5. So we should have a point at negative 4, negative 5. And we can draw in our second branch. So here's our reasonable approximation of our graph. Our domain will be the set of all x values such that x does not equal negative 3, where the vertical asymptote is, and x does not equal 2, where our whole is. The range is the set of all y values such that y does not equal 0, where our horizontal asymptote is, and y does not equal 1, which is the y value of the whole. Okay, one last example. F of x equals x squared plus x minus 12 over x minus 4. So factoring, we get x plus 4 times x minus 3 over x minus 4. To find the coordinates of our whole, let's set, well, we had nothing that canceled, so we can't set anything equal to 0, so we have no whole, or no removable discontinuity. To find our vertical asymptote, let's set x minus 4 equal to 0 and solve for x. X equals 4. So we can draw a vertical dotted line at x equals 4. Our x-intercept will set each factor of the numerator equal to 0 and solve for x. So first we get x equals -4, then we get x equals 3. So we have two x-intercepts, one at -4 and one at 3, and we can plot both of those points. Y-intercept. Let's put 0 in for x, or substitute 0 in for x. Y equals 0 plus 4 times 0 minus 3 over 0 minus 4. 4 times -3 over -4, which is 3. So we have a y-intercept at 0, 3, and we can plot that point. Let's look at degrees. We have a degree of 2 and a degree of 1. So the degree of our numerator is 1 more than the degree of the denominator. So for our horizontal asymptote, we will need to divide. Sorry, we don't have one because the degree of the numerator is 1 more than the degree of the denominator. We will have an oblique asymptote, and that is what we need to divide for. So we're dividing x squared plus x minus 12 by x minus 4. X times what is x squared? X. So x times x is x squared, x times -4 is -4x. We will subtract, so I will change the signs and add. X squares cancel out. X plus 4x is 5x. Bring down the minus 12. X times what is 5x? It's positive 5. 5 times x is 5x. 5 times -4 is -20. We will subtract, so I will change all the signs and then add. 5x's cancel out. -12 plus 20 is 8, and that is our remainder. So our quotient is x plus 5. So our oblique asymptote is at y equals x plus 5. So we will go back on the previous screen and graph that again. Okay, so I plotted our oblique asymptote by first plotting the point 0, 5, which was our y-intercept. I used the slope to rise up 1, go over 1 to the right, and then I kept going and graphed multiple points and drew in our oblique asymptote as a dotted line. So we can see where we have one branch, and it's going to look strange. So I have a branch that is curved like this, and I don't know how far in it goes, but then we'll have another branch. And to double check where that branch is, we need to calculate the value of the function when x is greater than the value where we have that vertical asymptote. So we have a vertical asymptote at x equals 4, so we are going to calculate in a moment f of 5. Okay, so where we have room here, let's calculate f of 5. So substituting in 5 for x, we have 5 plus 4 times 5 minus 3 over 5 minus 4, which is 9 times 2 over 1, or 18. So we have a point at 518, which is way above our graph. So if I go back to that last screen where we can see the graph, we know that we have another part of our graph up here. And of course, it's not going to cross or touch the asymptotes. So that is our graph. And now we'll go through and identify our domain and range. So for our domain, the only x value that we will exclude is where we have our vertical asymptote at x equals 4. So the set of all x's such that x does not equal 4. Now, our range is much more difficult, and we are actually not going to go through and calculate it here. So there are most likely some y values in this example that are excluded, but we would need to go through and actually look a lot more carefully at the function.